Hello and welcome back. This session covers the overview on slope failure modes and analysis methods. Before we start learning how to design log slopes, we need to know the typical types of log slope failure and the available methods to analyze those failures. The purpose of slope design is to ensure the log slopes are stable and safe against all types of failure. There are several types of slope failure. Circular failure is a common and a general slope failure mode for soil, but is also a failure mode in rock slopes. It usually occurs in very highly fractured or very weak rocks with no identifiable structural patterns. When rocks are very highly fractured or very weak, they behave like soils. Slopes of those poor and weak rocks also fails like soils. For circular failure, the slope fails along a circular failure plane across the slope, as shown by the photo on the right. The slope fails along the circular sliding plane through very weak and highly fractured or weathered rocks. You perhaps have already learned in soil mechanics that circular failure is a commonly assumed slope failure in soils. When soil slope fails, soil slides on a circular failure surface of least resistance. The same assumption is used in circular failure of rock slopes. When circular failure occurs, it is assumed that the rock mass slides on a circular failure surface. That circular failure surface has the least resistance through the slope. The sliding is controlled by the shear strength of the rock mass. Circular failure of rock slope can use the same slope analysis methods as those for circular failure of soil slopes. For example, the limited equilibrium slides method. Numerical methods modeling, for example, finite element methods, are also commonly used for this type of slope analysis. However, the parameter used for rock slope circular failure analysis must be rock mass parameters. As we learned in rock mechanics principle classes, rock masses are characterized by discontinuities, such as joints and bedding planes. If a bedding plane or a joint set cut through the slope as shown in the drawing and the photo here, we will have plane failure. Plane failure occurs in rock slopes when rock discontinuities, such as bedding planes and joints, are dipping in more or less the same direction of the slope, but with a gentle dip angle. In this situation, the discontinuity are daylighting on the slope face. Here, daylighting means the bottom end of the discontinuity can be seen on the slope face, as illustrated by the drawing below. Plane failure is governed by two main factors. One, the orientation relationship between the slope and the sliding plane. And 2, the frictional resistance of the sliding plane against sliding. The analysis of those two factors can be represented by the projection method. The illustration on this slide shows the analysis of a plane failure by the projection method. Here, the sliding plane is in red and is almost parallel to the slope plane that is in blue. The sliding plane has a smaller dip angle, so the sliding plane daylights on the slope. The frictional angle shown by the green of the sliding plane is smaller than the dip angle of the sliding plane. This means the sliding angle is greater than the frictional angle, and therefore sliding will occur. From the analysis by projection method illustrated here, plane failure will occur since both conditions of plane failures are satisfied in this case. We will learn about projection method and the slope analysis using this method in a later session. Plane failure analysis can also be carried out using analytical methods. It is done by examining the force diagrams illustrated here. By resolving all the forces acting on the slope into components parallel and normal to the sliding plane, we can calculate the shear resistance along the sliding plane and calculate the factor of safety. The factor of safety is a ratio of shear resistance to sliding force. If the factor of safety is less than 1, the slope will slide and fail. Analytical method can also allow for additional loads, including groundwater pressure. Rock mass usually contains 2, 3, or more joint sets. Those joint sets cut the rock mass into wedges and blocks. As shown on the slide, a daylighting wedge is formed by 2 joints cut the rock on the slope. One joint set is cutting into the slope from the right side, and you can see a large plane of the right side of the intersecting line. The other joint is cutting from the left, and you can see more parallel joints to the left. That wedge has slided and gone down the slope. This type of slope failure is wedge failure. It occurs on rock slope when daylighting wedges are formed on slope by the intersecting discontinuities. Similarly, a daylighting wedge is a wedge with its bottom end appearing on the slope face. This is in fact the intersecting line of the 2 joints planes daylights on the slope. Wedge failure can also be analyzed by the projection method. It is of course more complicated than plane failure, as it involves 2 intersecting joint planes and the slope plane. This is why on a joint you see 3 curves, each representing a plane. The blue is the slope plane, and the 2 reds are joint A and joint B. The red dot represents the line of intersection of the 2 joint planes. The red dot is on the same side of the slope and has a smaller angle Therefore, the line of intersection daylights on the slope. At the same time, you also see that the dip angle of that line of the intersection is higher than the friction angle. The result is that the wedge will slide down along the line of intersection. I will not explain the analysis here in detail, as we will learn it later. Here, I just want you to see how the projection method can make the three-dimensional analysis simpler. Wedge failure analysis can be carried out using analytical method. The general approach is similar to that for the plane failure analysis. However, because it involves more planes, it requires more complicated force equations. Many assumptions are needed to make the analysis simple. Such analysis is only carried out when a specific wedge is identified. With the development of discontinuous numerical methods, block element numerical modeling can be employed to analyze block and wedge stability. Rock mass can be cut by vertical or steep dipping joint sets. The rock mass then has a columnar or block structures, which may suffer from toppling failure, as illustrated in the slide. Toppling failure differs from sliding failure. It does not slide. The blocks on the top of the column tilt over or tip over and fall down. As toppling failure is represented by tipping over, it is therefore governed by the geometry of the block shape and the resultant body force. As shown in the diagram analysis below, when the body force W is inside the width B, the block will not tip over. Only when W line is outside the width B, the block will tip over around its base corner. Toppling failure can be analyzed through shape analysis, as illustrated in the diagrams on the right, with the 4 cases. It is governed by the relationship between block width height ratio B over H, the tilt angle phi, and the base friction angle phi. Please read the diagram carefully to appreciate the 4 cases, particularly the 2 lower cases where toppling can occur. Toppling failure can also be analyzed by analytical method. As an example here, shown on the right, analytical solutions can be obtained from column toppling failure by examining the intercolumn forces. Again, assumptions are needed, and including the interface intercolumn forces. Do you still remember rock mass rating, the IMR? It was taught in the rock mechanics course. IMR classifies the rock mass quality. We know that rock slope stability is related to rock mass quality. Slopes of good quality rock mass are more stable than that of poor rock mass. Therefore, rock mass quality can serve as a basis for slope stability assessment and the slope support design. IMR was initially proposed for classifying the rock mass quality for underground works and mines. It was later further modified for slope stability assessment and the slope support design. I will cover the use of modified IMR for slope analysis in detail in a later session. It is a very useful practical tool for slope and stability analysis and the slope support design. Here is just a brief introduction to show that with IMR slope rating, column 1 and 2, slope stability or failure mode can be assessed in column 3 and 4, and support design are proposed in column 5. I'm concluding this session by giving you the slope stability analysis flowchart proposed by Hook and Bray. You can find the original chart from the book by Dr. Eva Hook and Dr. John Bray, titled Rock Slope Engineering. It is indeed a classical book on rock engineering, and I urge you to read through the book, particularly if you are keen to learn rock slope analysis and design. As I mentioned before, we will learn more on rock slope analysis, design methods, and the construction techniques in later sessions. Goodbye, and see you later at the next session.